Well, good morning to all of you on this Tuesday that we're pretending is a Monday. Um, what we do today will be something of a review from last time, and also what we do should be helpful in terms of practicing some of the synthesis stuff from the last unit. You'll recall that in our discussion on dyes and chemotherapy and so on, that we talked about a strategy for making what's called an Aerodiazonium salt. And it's kind of an involved set of reactions in the sense that first you have to install the nitro group on the benzene ring. I guess let's start with benzene, which you do through those nitration conditions, HNO3 and sulfuric acid, nitric acid, and sulfuric acid, install the nitro group. Then you reduce that nitro group to the amine to get aniline using hydrogen and palladium on carbon. And then you use what we called diazotization, whatever, not sure how to say it, with NaNO2 and HCl, and that adds another nitrogen oops, the formal charge isn't there, sorry. And this is our Aerodiazonium salt. And if that doesn't look familiar, that's okay. I know you're worried about something else pending right now, so but you'll know where to come back to remind yourself of this. So there's a couple of different things we can do with the Aerodiazonium salt. One of them is just substitution reactions. And the good news is for none of them we're gonna worry about the mechanism. Though I might draw it here just to show you, for those of you who are interested. Sometimes I feel like if I don't see the mechanism, I can't understand the reaction. So you can do substitution reactions by providing a nucleophile that will replace the diazonium group. So if you use water, or I suppose OH, you can replace the diazonium group with hydroxide, and then nitrogen is the leaving group, which is, of course, a neutral gas, and it bubbles off and you're done. The mechanism in general for this kind of thing, I'll just show you off to the side, is going to be a class of mechanisms that we won't really talk about, but they are important in the pharmaceutical industry. Nucleophilic aromatic substitution. And the idea is if you have a sufficiently electron-poor benzene ring, you can have some nucleophile attack the ipso carbon to get a high-energy anionic intermediate in which you have broken aromaticity. Let's suppose it's negatively charged. Okay, and so you might imagine this reaction works well if you have an electron-poor benzene ring. You can see that if I had, say, an electron withdrawing group right here, it might be particularly good because that would stabilize the negative charge. But in any case, the electrons can kick back down, nitrogen can leave. So it's sort of an addition-elimination mechanism. Again, I'm not going to hold you responsible for that. You're not going to see it. It exists and it's out there, but if you're sort of worrying and wondering how this reaction happens, that's how. FYI only, I hereby promise not to test you on this mechanism. Okay. So, what else can you put in place of the diazonium group? Just about anything, though it looks like it looks like the halides themselves are not good enough on their own because the Aerodiazonium salt is stable, but if you add copper 1 chloride, you can replace the diazonium group with chloride. And so presumably, and your text doesn't say, and I actually don't know what the copper does, but presumably it's necessary because otherwise you just go ahead and do the substitution reaction at this stage. Now, you might wonder, why on earth would I bother to do this when we have a direct chlorination kind of reaction? And the answer is you may want to have different regioselectivity. So let me see if I can think of an example. So let's see. Suppose you had a nitro group, and what else would we want to put there? And then suppose we did this process where we first reduce to the aniline and then do the diazotization. And then in the last step, no, you know what? That wouldn't make sense anyway. Sorry about that. I was just thinking off the top of my head, and I was realizing that in the end we were going to get a product that I could have gotten anyway through an easier method. So I'm not sure why you'd want to do this. This making the phenol is particularly useful because we haven't figured out a way to make the phenol yet. More useful than these is a couple of reactions that allow you to make the iodo and fluoro derivatives, which we haven't been able to do before, in part because the fluorination reaction through the electrophilic aromatic substitution mechanism would have been way too reactive and violently explosive. So the reagent to use if you want fluorine is a weird reagent, HBF4. So just for your information, I guess, BF4 is an anion on boron. Where is the H? Well, we've told you before, there's no such thing as a proton on its own. So fluorine's more electronegative than boron. So this negative charge has to be felt more out on the fluorines. And so probably that H is on one of the fluorines. And I'm not sure what the mechanism is at this point, and your text doesn't say, so we simply won't worry about it. My guess is that one of the fluoro groups leaves, but I'm not sure. So I'm sorry that I don't have better information for you there. That doesn't mean that it's not out there, that people don't know it, but it just means that I don't know it. And if I don't care, you don't have to care, right? So if you use just an iodide salt, like sodium iodide, you can install the iodo group. So these are the two sort of useful ones, and the phenol that we would not have had any other method to install. So if you see that functional group on a benzene ring, and you have to do a synthesis, and you have to start with benzene, this pathway is sort of the only tool you've got to do it. Yeah?
Do you need sodium, or could you use the copper as well?
Do you need the sodium? Could you use the copper? I don't know. Presumably the copper would work. Your text points out you can use potassium iodide. My guess is that sodium or potassium iodide are easier, cheaper than the copper reagent. I minus is actually a pretty good nucleophile, so maybe it's okay without the copper, but this is hand waving because I don't really know. Okay, others? Okay, so let's do a practice problem. So starting from benzene, let's make metachlorophenol. And so sometimes you can plan a synthesis from the beginning. Other times it's better to sort of walk your way backwards step by step. So what could this phenol group have been previously? Yeah, it could have been the N2, the diazonium salt. Okay. And keep in mind as we're thinking backwards, I mean, we know how to put on the chloro group, right? But we need to figure out in what order to put the chloro and in what order to make the diazonium salt because we've got meta selectivity here. And that's a problem because if we put the chloro group on first, we would have had ortho-para regioselectivity. And if we had put the OH group on first, we would have also got ortho and para selectivity. So we need an electron withdrawing group somewhere along the line. And fortunately, we've got one because you get the aerodiazonium salt from the aniline. But even then, you've got a problem because it's an electron donating group. I think somebody might ask, could I have at this stage installed the chloro having already had the diazonium salt? I don't know, but your text doesn't really show that. So it's possible that that reaction doesn't work. In any case, you can go back one step further to get the nitro group and the chloro group, and then it's pretty clear, right? You would have put the nitro group on first and then the chloro group. So if we plan this out, then the thing to do is to check and see whether it works in the forward direction. So turn this into just a predict the products question. I've got my donating group here. I've got a resonance donor that would be ortho and para selective. I have the nitro group that's meta selective, so probably I want to put the nitro group on first. So reviewing that chapter 20 reaction, I'm going to do the nitration. Then, before I reduce to the aniline, this is where I want to introduce the chloride so that I can get meta-selectivity. So this is the aryl chlorination reaction from chapter 20. Now that I have the meta arrangement, I can do all the other stuff that we've done previously. So that would be reduce to the aniline, then diazotize, and then add water. And I'm going to just, in my mind, I think you'd want to add like basic water like hydroxide, but your text says water's good enough, so we'll stick with that. And that gives you your desired product. Okay, any questions about how we reasoned our way through that? Yeah.
For the OH group at the beginning, could it have been a carboxylic acid and you reduced it to an OH group?
For the OH group at the beginning, could it have been a carboxylic acid and you reduced it to the OH group? If you had had, say, something like this, oops, I think you're asking about this as a precursor. Oops. And the answer is you could reduce that carboxylic acid with lithium aluminum hydride, but the carbon doesn't go away. You've still got that carbon there. Yeah. Yep. What else? All right, others. Let's try another one. Some of these will be easier than others. Let's try Paraidotoluene. So, take a minute and see if you can plan out a synthesis. You got to make it from, this is the desired product, and you got to make it from benzene. Pay attention to the relationship between the groups and make sure that you can get the desired regioselectivity via your method. I did that once during and it was actually stressing the students out. They're like, I don't know. That's the Jeopardy theme song for those of you that aren't aware. Getting close. Need more time. More time. Okay, so I'm gonna get us started. You can either think backwards or think forwards, but any ideas? Yeah, go ahead. You start with Friedel Crafts. Good, and why did you begin there?
Because you need to add on the methyl group, and so that's one way to add that on.
Okay, that's one way to get on the methyl group. How do you know you put it on at this stage, though?
Because if you were to do, in order to get the iodine, you have to go from an Aerodiazonium salt, which means
Okay.
you have to have NO2 at some point,
Right.
and that would result in if you added it on, but we need to compare that between the two.
Okay, good. So the idea is that when you see the iodo group, right away you're thinking that used to be NO2, which is a meta director. And because the iodo group is para, then you want that. Yeah, go ahead.
But can't you, like, since that's like intermediate, can't you just put on the methyl after you take off the NO2?
Could you put the methyl on after you replace the NO2 with iodo?
Yeah, get iodo and then just have.
Yeah, presumably that would be an ortho and para director like the other halides. So I think that's a decent approach too. And you may find this as you're working on you may find this as you're working on synthesis problems from the text. You may come up with a method that is slightly different than the text, and I know that's troubling to you because I've told you to pay attention to problems that you get wrong. But it's possible that your synthesis works just fine. And the standard on synthesis questions is always, hey, if your chemistry works, nobody's going to argue with you. So if you're in a situation where you're wondering, does my route work? Take a screenshot of it and send it to me or one of the TAs and ask, and we can, or tell a friend and see if they can find anything wrong with it. Because in these cases, there probably are, in some cases, there probably are multiple methods that would get you there. So let's see, I'm putting in making the diazonium salt and then finally potassium or sodium iodide. Okay, and then your alternative was, why not do the nitration first? Should put the NO2 group there. I was just going to copy that stuff above, but in the interests of not driving those of you who are using paper crazy, we will just write this out. And then, once you put the iodo there, can you then do the Friedel-Crafts reaction? And I think so. I don't see anything wrong with that. Oh, wrong Lewis acid, but whatever. Okay, any other potential routes? Anybody or any questions you want to ask about that one? Go ahead.
Could you also add the aniline first and then add methyl after that?
Oh, right. So could you along the path, once you had gotten to the aniline, so this is the proposed alternative. You get to the amine, then at that stage do the Friedel-Crafts reaction. I would have allowed that totally fine. Your text points out that anilines are a little tricky to use with the Friedel-Crafts reaction because the amine is nucleophilic enough that it will bind your Lewis acid, and that prevents the alkyl chloride from getting activated. Nevertheless, I've chosen to ignore that, so that would have been a totally fine answer. Yeah?
Just a question about iodine. Could you have used electrophilic aromatic substitution to add iodine? Like I2 with FeI3?
Could you have used electrophilic aromatic substitution to add iodine? And the answer is no. There's not a good reaction. Sorry, I'm trying to draw and talk at the same time, which is always a challenge for me. So, yeah, the question is, could I not have installed the iodo directly with this reagent? No, I don't know why, but that doesn't work, presumably. Yeah, and I'm not totally sure why. Okay, other questions? Okay, let's try this one. What's that? Oh, yeah, sorry. Deer in the headlights there for a minute. I was like, what? Yep, starting with benzene. And if at this point you don't want to rewrite a bunch of stuff that we've written previously, you can just draw a single arrow. I'm fine if you want to do something like this. C above and then get to something like this. Like, you can abbreviate because there's no need to write out the same thing like again and again. But make sure you point the arrow to the series of reactions that gets you there. Okay? For those of you watching this days later on YouTube, don't skip ahead to get the answer. Pause it or whatever and make sure you actually do the problem. Okay, got anything? Oh, sorry, this is one of the, I told you about these. This is on your last exam. These are the nanoputations. Yeah, just go look it up on Wikipedia. There's actually a research group from Rice University that was doing this, and I think it was mostly about making chemistry cool to kids. My son, who's in general chemistry, was entertained by this. Like, it's sort of pointless, but kind of cool. They've actually made nano cars for these nanoputations to ride in. They can't actually get one in the car to drive it, but they have made cars that actually roll along surfaces. Anyway, my son Nate was impressed with the jazz hands T-butyl groups. And we'll actually learn how to do some of these reactions later, but you could make this portion down here with the Friedel-Crafts reactions, though the meta-substitution might be kind of difficult. So anyway, what have you got for this problem here? Yeah, go ahead.
You start with the Friedel-Crafts substitution to get a methyl group.
Okay, so you want to put the methyl group there first. Though there's not a methyl group in the product, so what are you thinking there?
So, well, I would first
Okay. So,
And then at the end, I would use KMNO4 to make the carboxylic acid.
all right. So we're going to use diazotization. See above. That's this sort of 3 reaction series. Well, where first you install the nitro group. Dang it. I don't want to abbreviate lest anybody be confused when looking at the notes. So we're talking about putting in the nitro group. And you got to do that after you install the meta group so you can get, after you install the nitro group so you can get meta select. Oh man, this is really, I'm really struggling. So now I have to just go through it slowly. Slow down. You got to put the nitro group on second because you need the nitro group to be para to the methyl group. Then you can do this series where we first reduce to the aniline, then make the diazonium salt, and then what am I going to do?
Use like a sodium methoxide.
Sure. Sodium methoxide to install that OME group. And then what? Then yeah, we've learned this KMNO4. I always feel like I'm saying the alphabet when I say that one. LMNO, KMNO. Anyway, KMNO4, yeah, we'll oxidize that methyl group to the carboxylic acid. All right. Other alternatives, other approaches. Yeah, go ahead.
Instead of oxidizing, could you just unfriddle crash and put a CL at the end there?
Okay, so yeah, this is an interesting question. So the idea, let's delete the nano kid. Your idea would have been to get through similar methods to get here. And then what?
And then friddle crash with a CL on
So you're wanting to do AlCl3 and this? Okay. Anybody else thinking that too? Yeah? So I would have allowed that. This is called, what is this called? Chloroformic acid, and it's pretty unstable. The reason for that is that as soon as that proton gets removed, and it's actually pretty acidic, you are now set up for a decarboxylation reaction where you get CO2 because electrons on this oxygen kick down and kick off Cl as the leaving group. So I would have allowed it, but in practice it probably doesn't work. So that's why I would have avoided it, but I certainly wouldn't have counted it wrong. Or rather, I've had people do similar things before, back when I gave free response tests and the graders counted it wrong and they came back and I told them what I just told you, but then I felt bad and so I gave them the point. So that would have been fine. But in practice, yeah, that reagent is too unstable, which is why I didn't list it as an option. Okay, go ahead.
Could you do it with an ester and then reduce it with H3O plus?
Okay, so could you use methyl chloroformate? Is that sort of,
Yeah.
would that work? That's not a bad idea. I mean, this reagent definitely exists, and if you put the Lewis acid on it, presumably you might get this ion, which could then be the electrophile in the Friedel-Crafts reaction. So yeah, I mean, certainly if I'm going to allow this, I definitely have to allow that, and I like that. It's a pretty creative way to get rid of the decarboxylation problem. Yeah, go ahead.
Does it matter if you do the KMNO4 before or after you add the NaOH?
Right. Does it matter if you do the KMNO4 before or after you substitute out for the diazonium group? Um, I don't know. I think probably not. Certainly not. I can't think of anything in the text that would tell you that that's not the case. I personally would be a little bit worried about it because anytime you see the ability for nitrogen to come off a compound, you're I'm already thinking, okay, well, I better move on to the next step quickly, because I don't know how shelf stable that reagent is, and KMNO4 oxidation is pretty vigorous, so I just don't know what would happen, but it would have been fine. I would have accepted it as an answer, so that's good. What else? Yeah.
I'm a little confused on how the methoxide would be an electrophile.
So the methoxide, how is that? And we're back. So your question was about this stage?
Yeah.
Okay. Yeah, so it's not actually acting as an electrophile at that point. Before that reaction, we have methyl, and then we have diazonium group. And remember, the methoxide is actually going to act as a nucleophile, attack the carbonyl carbon, or I'm sorry, attack the ipso carbon to get the intermediate, and then, oops, I needed to do something different with those electrons. Then electrons kick down and nitrogen leaves rather. So yeah, it's acting as a nucleophile there, you're right. Okay, yes?
Are there limitations on like how strong that nucleophile needs to be to be able to kick off that?
Yeah, that's a great question. Are there limitations for how strong that nucleophile needs to be to kick off the diazonium group? And the answer is, I don't know. If you look back at the conditions that they're suggesting, it seems like water must be okay, but I don't get that because the diazonium salt would need to have seen water before, so chances are it needs to be OH minus. I'm just sticking with what your book said. Presumably Cl minus isn't good enough on its own because you need the copper. Presumably I minus is good enough on its own. I minus is a pretty good nucleophile owing to its large size and polarizability. So I'd say what we're looking at here is a bunch of empirical results, and we're not trying to derive any principles for what the nucleophile needs to be. So, you know, I like that we said, whoa.
So how would we know that methoxide is good enough?
Well, you by analogy, you'd look, oh, water's good enough. Well, methoxide's certainly more nucleophilic than water, so probably methoxide's good enough. If you had used methanol, we would have probably also said that's just fine. Yeah.
So as a general rule for that step, you put sodium and then whatever you want to substitute.
Is it general for that step you can put sodium and then whatever anion you want to substitute? Yes, but presumably not the chloro and the bromo because you need copper. I don't know. That's always frustrating to me. And remember, you got to remember where the text comes from. Professor Smith is a synthetic organic chemist, and what that means for us is just that synthetic chemists often are willing to use a reaction even if they don't know all of the mechanistic details, which we're comfortable with in other aspects of our life. Enter really probably reaching spiritual analogy, but we can all use the atonement without knowing precisely how it works. And in the same way, you can, sorry, it's really, yeah, we can use copper, the copper chloride method to, yeah, okay. But what I'm saying is that there are things that are useful that we nevertheless don't understand in all the details. And what I'm saying is I don't know why we need these. It's possible the information exists in the literature. I haven't cared enough to go look for it. So anyway, I'm sorry. That was a real stretch. Okay, other questions? So now let's, I think I told you at the end of sort of last class, one other thing you can do with diazonium salts, and that is coupling reactions with electron-rich arenes. So let me give you an example of this. Once you have the diazonium salt, that can be an electrophile for an electrophilic aromatic substitution reaction. And Y here needs to be a strong electron donating group, such as N2 or NHR or NR2, where R equals alkyl. It could also be OH or OR. And what happens is para substitution is preferred, presumably. Well, actually, I don't know that. So we're going to show the para products, but the ortho products would probably also be reasonable. We'll have electrons attack the nitrogen, moving these electrons from the nitrogen-nitrogen pi bond down onto the positively charged nitrogen so it can be neutral. When we do that, we get this intermediate. And then a base can remove a proton, and then we restore aromaticity. And the reason we would want to make this diazo compound is because these can be very, very colorful. And as we talked about last time, dyes can be very useful. All right, so now we can make what were bad synthesis questions even worse. So I'm going to draw a diazo compound. I think this one is red, I don't know. And let's just talk strategically how you would do this. A coupling reaction is a reaction that brings together two parts into one. Usually in a coupling reaction, you do that at the end. You might imagine, well, why couldn't I have made the diazo compound and then installed the sulfonyl group? And the answer is, once you have two benzene rings in the molecule, how do you control which one gets what you're going to do? So you functionalize your benzene rings first, and then you couple them together. So when looking at a product like this, and I'll just put up here, usually you want to do the coupling reaction at a late stage after all the functional groups are in place. We need to decide which of these bonds between carbon and nitrogen did we make? Did we make that one or that one? And the principle your text uses relies on this electrophilic aromatic substitution reaction. You want the diazonium salt to be the electrophile, and you want your other benzene ring to be the nucleophile, and you want it to be electron rich. So looking at this molecule, which side do you want to have been the nucleophile? The side with, yeah, you guys said right side, and I'm seeing you guys point that way, and I'm thinking, that's my left side. So, okay, got it. Yeah, you want the nucleophile to have been this portion so that the electrophile can have been the diazonium salt. So first, figure out which bond you're going to make, then think one step backwards through the coupling reaction. Think about what the previous reagents would have been. You have the dimethyl amino benzene, and then over here I should have the diazonium group and and the sulfonyl group. This is where, or the sulfonic acid group, this is where retrosynthesis, that is thinking one step backwards, is really useful. If you do a late stage coupling reaction, retrosynthesis, you step back through that coupling reaction, you see what the two parts were, and then you can synthesize. Then it's just two different synthesis questions. Then you just synthesize those two separately, right? So I'm going to rely on you to make both of these. That would be a decent practice to do in your notes, and I will put it. I will put the solution to this in the notes to today's lecture. But I want to give you one sort of more chance to think about a late stage coupling reaction and which side you would have wanted to be the nucleophile versus the electrophile. Okay, what do you think of this bond here and this bond there? Which is the one? So to your left, you're thinking that should be the what? So you want the one here to have been the nucleophile. So that means you need to have coupled phenol to, and then over on this side, what's it going to be? The other functional groups stay in place, and you need the diazonium group there. Okay, good. And again, it's now your task to make this and make this. The phenol should be easy. We've already done that. Here, you're going to have to figure out how to get this methyl group meta to the chloro group. That's sort of the big challenge there. Once you have the methyl and the chloro together, you can then put the nitro group here and then proceed to do the diazotization reaction. Okay, have fun. Good luck. See you tomorrow.